The second reaction in Module 6A, catalyzed by palladium, is known as the Suzuki reaction. This is a substitution reaction of an organoboron compound with an organic halide. Modern versions of the Suzuki reaction now accommodate virtually all hybridization patterns on the carbons, but the most common Suzuki reaction involves the coupling of two sp2 hybridized carbon reactants. In particular, the Suzuki reaction is an excellent method for the synthesis of 1,3-dienes. The Suzuki reaction is also stereospecific with both of the reactants, so that an E or a Z vinylic boron compound will react with the corresponding E or Z alkenyl halide to produce the 1,3-diene with retention of alkene configuration. As described in the previous video, for the Heck reaction, the Suzuki reaction also typically uses a palladium-2 complex as a pre-catalyst, which under reaction conditions generates the active catalytic species in the palladium-0 oxidation state. During the class meeting, we will discuss the structure or structures of stoichiometric byproducts arising from the Suzuki reaction depicted above. Moving to the lower part of this page, we'll quickly review formal oxidation states and electron counting. The dichloropalladium bis-triphenylphosphine pre-catalyst has a formal oxidation state of +2 because of the two negatively charged chloride ligands and the neutral triphenylphosphine ligands. Palladium as a group 10 metal in the +2 oxidation state has 8 d electrons, so the valence electron count associated with palladium is 16 electrons, 8 d electrons plus 4 2-electron donor ligands. For the active anionic palladium catalyst, which has an overall negative charge, that negative charge corresponds to the anionic chloride ligand, so that the formal oxidation state of palladium is 0. With 10 d electrons on palladium 0, the valence electron count of the active catalyst is also 16 electrons. We'll now turn to the next page of the worksheet, which shows the first few steps of the catalytic mechanism. The mechanism that is shown in the textbook was long accepted and only recently has been disproven. So the current accepted mechanism is shown here. The anionic palladium catalyst first coordinates with a pi bond of the vinylic halide. After this ligand association step to give intermediate A, brings the carbon-halogen bond into close proximity with palladium for the oxidative addition step to give intermediate B. The Suzuki reaction has long been known to require a basic additive. And we now understand mechanistically that a ligand substitution process with dissociation of halide anions followed by association of alkoxide ligands gives intermediate C. Continuing down the page of the worksheet, these are the remaining steps of the catalytic cycle. Step 4 is a Lewis acid-base reaction. One of the alkoxide ligands is nucleophilic, reacting with the electrophilic boron, generating intermediate D, which fulfills the octet rule on boron. This now sets the stage for a special type of ligand substitution, step 5, which is known as transmetalation, in which a carbon ligand is transferred from a more electropositive boron atom to a more electronegative palladium atom, in intermediate E. Transmetalation is also favored thermodynamically by forming a covalent bond between electropositive boron and highly electronegative oxygen. From intermediate E, the organic product forms by reductive elimination, which regenerates the palladium 0 catalyst for another round of the catalytic cycle. This is summarized on the final page of the worksheet. First of all, note that most of the intermediates involve 18 electron complexes. Only the reductive elimination to generate the active catalyst gives a 16 electron intermediate, which in a ligand association in step 1 returns to a stable 18 electron configuration. However, there is a change from palladium 0 to palladium 2 in the oxidative addition. Step 3 is a multiple series of ligand dissociation and associations, which I've grouped together as a ligand substitution reaction. Step 4, the Lewis acid-base reaction, can also be considered a ligand association step with regard to boron. Although step 5 might look like a ligand substitution reaction, we typically differentiate this by specifically calling it a transmetallation, counting both palladium and boron as metals. We'll conclude the video with a question. This is the structure of the 8 complex, which was originally thought to undergo transmetallation with palladium. To test the role of the 8 complex in the mechanism, researchers added this boron 8 complex to a catalytic mixture for the Suzuki reaction. If this complex was involved in the reaction, one would expect that increasing the concentration of this reactant may increase the rate of the reaction, to the surprise of those that adhered to the old mechanism. increasing the concentration of this 8 complex actually slowed the rate of the Suzuki reaction. So this required rethinking the mechanism. In class, we'll discuss the reasoning consistent with this evidence. This concludes the Module 6A video on the Suzuki reaction.